Hello Year 10, this is the second topic of GCSE Double Science Physics, Generating Electricity. Please first fill in the front page of your booklets. You can see that this is the second of 5 topics and you'd have already studied electric circuits. Page 1 has the equations on as usual, which you can refer to as needed. Page 2 is for teacher feedback, and we're going to start today on page 3. Lesson 1, Power Stations, is the title, and please write down today's date. So just write that down, Lesson 1, title Power Stations, and today's date. Press pause, and when you've written that down, press play. This is what you need to learn in the topic, and in today's lesson we're going to be learning statement C, which is all about the processes involved in generating electricity in a fuel-based power station. So that's lesson 1, pages 3 to 9 in your booklet. So, a quick starter. We take electricity for granted. I'm using it now, of course, to produce this video. Describe the impact on your life if electricity, including batteries, to power smaller devices, such as mobile phones, was not available to you for a week. Maximum answer, 50 words. So think about your day-to-day, where you use electricity and how your day would have been different. So this is just a starter to get you thinking. 50 words, so if you can go for at least 4 or 5 lines, say how your life would be different, and 3-4 minutes should be sufficient. Start now, so press pause on the video, and when you've completed, press play. Okay, so that should have been a personal reflection, and you think about the importance of electricity in modern day life. We're going to look at 3 other reasons why electricity is in such demand and so important. Reason 1. Electricity is a form of energy like heat and light, but unlike other forms of energy, it's quite easy to transform, change, into other forms of energy. As such, it's easy to use electricity to make other more useful forms like kinetic energy and sound energy. Just to put that into context and for you to gain a deeper understanding and appreciation of that, what I'd like you to do is to complete this table. Now when you're completing this table, there's one that's been started there on the screen for you. I'd like you then to use 2 keys, ideally highlighted at 2 different colour pens, as you can see on the screen there, to show which forms of energy are useful and which are wasted, because we're going to be learning more about that later on in this topic. And I'd like you to do it for 4 different appliances, and you've got them written down there. The first one has been done for you, as I said, TV. Now if you think of a TV, light comes out of it, that's how we see images on the screen, and sound comes out of it, because we listen to what comes out of the television as well. But a byproduct of the process of producing that light and sound is that we also produce heat energy, which is wasted energy. So if you can copy down in your booklets what's on the screen, and then write down the types of energy electrical energy is transformed into for the toaster, the hairdryer and the washing machine, and then use your own key to show which is useful and which are wasted. Press pause now. When you've completed the table, press play. Okay, now I've completed the table, and what I haven't done yet is just highlight the useful forms of energy So the toaster heat to toast the bread. In a hairdryer you need warmer, and that air needs to move towards your hair. And in a washing machine, heat up the water, and kinetic to turn the drum of the washing machine around. So what's left over, of course, are the wasted forms of energy. There'll be a bit of light as the wires in the toaster heat up, and the hairdryer makes sound, as does the washing machine. If you turn on to the next page, it says summarise reasons 2 and 3 in the line paragraph. Remember, we just looked at reason 1, and the reason why electricity is so important is that we can turn it from one form into another. Now reason 2 and 3 I'm going to put up in the video now, but then I'd like for you to turn that into your own words and to complete 2 paragraphs, writing down reason 2 here and reason 3 here. Here are the other 2 reasons, and what you need to do is write this down, paraphrase it into something that makes perhaps more sense to you. I'll read through both reasons. Electricity is relatively easy to move over long distances. Electric current travels well through metal wires, which makes getting electricity from one place where it's generated to a place where it's needed very simple. So that's all about moving electricity. And reason 3, electricity is easy to generate from other forms of energy. Power stations burn a fuel, which eventually produces electricity. Okay, so your job now then is to write reason 2 and 3 down there in your own words. Press pause now and press play when completed. Now that we've gone over the importance of electricity in everyday use, we're now going to look at how electricity is generated when a fuel like coal is burnt. And a little starter for that, before we get into the nitty-gritty of that exactly, is I'd like you now to, if you're in class, or if you're at home, it might have to be something you do with a member of your family, or a phone call, discuss what you and your next door neighbour, so that's if you're in the class, think the answer might be, and write it down in the box below. How on earth do we turn coal into electricity? Big black lump of stone into electricity. Press pause, complete, and when you have completed, press play. Top of page 5, this activity is a question and answer activity, and it's going to help you gain an understanding of how not just coal, but coal, oil and natural gas, 3 fossil fuels, are turned into electricity. So what you need to do, as I've shown here, is fill in the gaps between the questions, and I will let the video run. So make sure you've got a pen handy, watch the video. It's 20 minutes, and I'll go over the answers with you at the end. Now, as you'll see in a moment, it's quite an old video, probably taken from the early 1980s, but the relevance of the technology of power stations is the same now as it was then in how the power stations work.
Britain's best-loved soap opera Coronation Street is just finishing.
Would you like a cup of tea?
Yes, please.
At the end of that programme, there's a sudden surge in demand for electricity as kettles all over Britain are switched on. How is all that extra electricity suddenly made available?
Hello, Dynamic National Control here. Could you generate 240 megawatts on number 2 machine, please? Thank you.
Believe it or not, there's a power station in this mountain. That's where the extra supply comes from. The power station can be switched on and will generate full power within 15 seconds. But it's the only one of its kind in England and Wales, and it's only ever used as a last resort, when there's an exceptional need to provide extra power for a short period of time.
I will stop the video there because the information we just covered would help you answer the first question. Now the first question here, what type of electricity generation only takes 15 seconds to start to produce electricity? It didn't actually give you the name of this type of electricity generation and the type of power station. So hydroelectric, I'm going to write that down for you. Hydro has to do with water. Hydroelectric. Try that again. Hydroelectric. Is the type of electricity generation that takes 15 seconds to start. So the thinking there is, there's a sudden surge in demand. We need extra electricity for the country, and that's when that power station is switched on. Norwig is the name of that particular power station. And what I want you to do now, I'm not going to stop and go through all the answers again, because you should be able to work the answers out yourself and answer them as we go through.
Think of the millions of homes in Britain. Then think of all the things in those homes that use electricity. Where does all the energy come from? Generating a little electricity is simple enough. When a magnet is introduced into the centre of a coil of wire, an electric current is induced in the wire, but only for as long as the magnet is moving. When the magnet is withdrawn from the coils, current is induced in the opposite direction. The faster the movement of the magnet, the bigger the current in the wire. If the magnet is moved rapidly in and out, the current keeps changing direction. It's an alternating current. This equipment is a simple generator. Generating electricity is all about converting energy from one form into another. Here, kinetic energy, the movement of the magnet, is being converted into electrical energy in the wire. The electricity that we use in Britain is supplied from more than 70 power stations. They all have generators on a grand scale, which convert kinetic energy into electrical energy. Where does the kinetic energy, the movement, come from? It comes from a turbine, which is basically a wheel, which will turn when energy is applied to the blades. In most power stations, the energy is supplied in the form of steam. This apparatus demonstrates the principle involved on a small scale. It's a miniature power station. The steam produced by boiling the kettle is directed at the turbine. It strikes the blades and makes the turbine rotate. The turbine drives the generator, a magnet moving in a coil of wire with many turns in it. An alternating current is generated. Notice the change in direction of the needle. More than 70% of our electricity is generated at power stations, which use coal as fuel to make steam. Coal is one of the fossil fuels, along with oil and natural...
I'll just pause the video there. This was made in the 1980s, and the amount of electricity now produced from coal has diminished dramatically since here. The percentage of coal that's being produced now is a lot less, and we'll look at that later on in this topic.
Gas. This is one of the biggest coal-fired power stations at Fiddler's Ferry near Warrington in Cheshire. The delivery train moves slowly through the discharge area without stopping. The coal falls into underground hoppers and is carried by conveyor belt to the coal store. The coal is already in small lumps, which makes for easier transportation and handling. A stockpile is kept in case of any disruption to supply. There are more than 400,000 tons here at the moment. The coal is crushed into very fine powder in these pulverizing units. That's done for two reasons. The smaller the pieces, the greater the surface area available for reaction during combustion. It also makes the fuel easier to handle. It can be blown with hot air as a fine powder through pipes and into the boiler furnace. In the furnace, the fine coal burns like a gas. All fossil fuels release energy when they are burned, combining with oxygen to produce a lot of heat, as well as some waste materials. The heat is absorbed by water contained in many kilometers of coiled tubing, which form the boiler wall. The water is turned into steam at high pressure. This is where the next stage of the process happens, the power hall. The blue machine is the massive equivalent of the little turbine of our demonstration. The steam from the boiler goes into a high-pressure turbine. It turns the turbine, but in doing so, gives up some of its energy. So it is fed back into the boiler to be reheated and used again to turn a low-pressure turbine. The orange machine is the generator. Inside the generator, linked to the turbine by a shaft, is the rotor, which is actually a large electromagnet. It turns at 3,000 revolutions a minute inside the stator, which has many coils of copper wire. The generator produces electricity at 22,000 volts. The power output of each generator is 500 megawatts, and at Fiddler's Ferry there are 4 of them, giving a combined total output of 2,000 megawatts. Once the steam has done its work and exhausted its useful energy, it has to be turned back into water so that it can be reused. That happens in the green pipes, which are the condensers. The water in the boiler system is very pure. It has to be like that to minimize any problems with corrosion in the pipework. The water in the cooling system is different. It's poor quality, so it's kept separate. A heat transfer system operates in the condensers. The steam from the turbines turns to water as it gives its heat to the coolant water. The coolant water is then pumped away to the cooling towers, which are a familiar sight at coal-fired power stations. The water is pumped in at around 15 meters up the tower. That's only a quarter of the way up. The height of the tower creates a powerful upward draft of cold air. The water is sprayed out through a sprinkler system. It is cooled by the cold air as it falls to the reservoir below. Often people think that the output of a cooling tower is pollution in the form of smoke. In fact, it's only steam. Around 30,000 gallons of it is given out every day. But there is a lot of heat going up into the atmosphere. Any water lost through evaporation in the cooling towers is replaced with water extracted from the nearby River Mersey. Let's look now at a nuclear power station, and there's an immediate difference from the outside. There are no cooling towers. That's because most nuclear power stations are built next to the sea or an estuary. This wheel filters the seawater to remove debris before it's used in the condensers as a coolant for the turbines. It's discharged back into the sea after it's been used. The turbine room, though, is similar to Fiddler's Ferry. In fact, the turbines and generators at the two power stations are almost identical. It's the method of generating the steam that's different. This is the reactor hall at the Hesham nuclear power station in Lancashire. It's the equivalent of the boiler house at Fiddler's Ferry. There's a fuel involved here, but no combustion. The fuel is uranium dioxide. It contains a radioactive isotope which can be split to release huge amounts of energy. This is the top of the nuclear reactor, and all the action takes place under here. In the process, the atoms of the isotope uranium-235 are bombarded with neutrons. The nucleus splits into two, and a great...
Now I'm stopping the video there because you don't need to understand this science or this physics until year 11. And the point, or the important point you need to understand, is that heat is being produced during the nuclear reaction, which warms up the water and turns the water into steam. That's the important part, not how that heat is being produced. I'll let the video run a little longer so you can see the similarities between a nuclear power station and the fossil fuel power station.
A deal of heat is given out. The heat is used to make steam in the boiler. The fission, that's the splitting of the nucleus, causes other neutrons to be released. Those neutrons then go on to collide with adjacent atoms of the isotope, and further splitting happens. When fission takes place in a series of atoms, that is called a chain reaction. In the nuclear reactor at Hesham, the fuel is in the form of pellets of uranium dioxide. The pellets are put into steel cans, which are then linked together to form a fuel element. 8 elements in line make up a fuel assembly. The fuel assemblies are surrounded by a graphite core, which is essential to the process. Nuclear fission, the splitting of the atoms, happens within the fuel assemblies. The graphite slows down fast neutrons that are released by fission. This makes them more easily absorbed by other atoms, so that a chain reaction occurs. If the chain reaction was allowed to go unchecked, the consequences could be disastrous. The heat would build up until the reactor melted. So a control mechanism is built in. The reactor core also houses control rods made of boron. Boron is capable of capturing fast-moving neutrons and absorbing their energy. So the rods can be raised or lowered to control the rate of the chain reaction. The heat from the fission is absorbed by carbon dioxide gas, which circulates through the reactor. For this reason, it's known as an advanced gas-cooled reactor.
So the important point I want you to understand and learn from this is that, again, water comes in, steam comes out. And in order to turn that water into steam, you need heat. And the heat in this case comes from a nuclear reaction. The steam that then comes out drives a turbine, that drives a generator, that produces electricity. So, going back to these questions, what I want you to do now is to compare your answers against these here. So question 1, what type of electricity generation only takes 15 seconds? I give you the answer to that, that's hydroelectric. Can you self-assess your work now please with a red pen? Name the 3 fossil fuels that could be used in power stations: oil, coal and natural gas. What is induced when a magnet is pushed into a coil of wire? That's an electric current, or I'd allow electricity. 4, what substance does the coal heat up and what does it turn into? So it heats up water and it turns it into steam. 5, the steam rises and turns a turbine. 6, the turbine is made of blades that turn and cause a magnet to turn inside a coil of wire. Together the magnet and the wire are called a generator. And question 7 is just the bottom of the screen. The generator transfers kinetic energy into electrical energy. I'll go over that last one again. The generator transfers kinetic, remember that's movement energy, kinetic energy into electrical energy. And that's really the real clever part of the power station. I was able to turn it from kinetic into electrical. When you finish that, just turn over on the page 6, which looks like that. I've just copied and rotated the image to the side, which shows the different parts of a thermal power station, which you've just learned about, and I give an additional explanation to help you complete this. And what you've got to do is fill in those 5 boxes. I've done 2 there for you in the video. So this is one piece of software that will help you gain a better understanding. And what you can see is you've got the furnace and boiler producing the heat and the steam. And that could be oil, gas, coal, or even nuclear. But the coal, oil and gas are the fossil fuels. And you can see then, if you click on the different parts, it explains, it's slightly off the screen, so I'll read it. The turbine, high pressure steam travels from the boiler through pipes to the turbine. As the steam passes through the turbine blades, it causes them to spin, just like wind blowing through a windmill. The generator, a shaft connected to the turbine, spins a powerful magnet inside the generator. The rotating magnetic field generates an electric current in the coils of wire surrounding the magnet. The electrical energy produced by the generator is delivered at around 25,000 volts. And finally, the condenser. The condenser, steam from the turbine is condensed back into water, which is returned to the boiler for reuse. A continuous supply of water circulates around the condenser to carry the unused heat away. Now that is also written down slightly differently there, so you can use either my verbal explanation or pause the video here in order to complete that. Okay, so pause the video when you've completed all those boxes. Oh, and by the way, what I'd like you to do is put in capital letters where there's a change of energy. Coal burns to produce heat energy. And what I could have done there actually is take that back a step further and say that the chemical energy coking coal is transferred into heat energy when burnt. Okay, so that's page 6. On to page 7. This is a self-assess. So what you need to do, the explanation, or I should say the instructions are here. Write the 3 words in speech marks next to the correct arrows. So there's 3 arrows and there's 4 boxes. So you can see you've got 3 in red, which are in speech marks next to the correct arrows, and then the words relating to types of energy. So the words relating to types of energy go into the correct box. So you've got 4 boxes and you've got 4 words remaining. I'll just do the first one. So we've got chemical turns to heat in the boiler. So we write boiler next to the arrow. Then we've got chemical being turned into heat in the boiler. So can you complete that? And when you complete it, I'll give you the answers and we'll mark together, or you mark your own. Okay, so as we go along, it might be just worth just crossing off the words that you've used. So after the boiler, we have the turbine and then the generator. So we get turbine, generator, and the turbine turns the steam into kinetic energy. So the kinetic energy really is in the moving steam, and then that kinetic energy goes into the generator and produces electrical energy. Alright, so just tick the ones you got right and correct the ones which you've got wrong. Next, bottom of page 7, what you need to do is read that paragraph and use that paragraph to help answer the questions below. So it's this paragraph here which I'm talking about, and there's information in there that's going to help you answer these questions below. Now this is the teacher assess part of the lesson, and question 1, for example, look, says provide a definition for non-renewable energy sources, and question 2 for renewable energy sources. And you can get the definitions here. Look, a non-renewable source of energy is defined as a source that, once it's used, cannot be created again. It's really important you understand the difference between non-renewable and renewable sources of energy are continuously being produced, mostly as a result of the action of the sun. So wood, for example, is sometimes classed wrongly by pupils, but because you can regrow trees, it's classed as renewable because it grows due to photosynthesis due to the sun. Question 3 is related to that because it's asking you to complete the table, a very simple table, 2 columns, renewable and non-renewable. And you've got to just list down the renewable sources of energy in the left-hand column, and of course the non-renewable things you can't renew in the right-hand column. And just to help with that, I know it says in the question to use the IWB, the interactive whiteboard, but I've just written down the different energy sources here for you. Now remember, these are called energy sources, right? They are sources of energy. That's where energy can come from. They are not what we would class as forms of energy. Forms of energy are your heat, your sound, your light, electrical, etc., etc. Sources of energy are where energy can come from to create electrical energy and other forms of energy. So that's question 3. Question 4 is the final question of today's lesson, because we're going to finish at the bottom of page 9. And you've got 2 pie charts. If we look at the one on the right hand side for the UK, it tells us how much energy, and I alluded to this earlier on in the lesson, looking at the amount of energy that's created from different... That's Alexa in the background, thinking I'm talking to Alexa, so apologies for that. I'll try again. I alluded to this earlier in this video. I avoided the word lesson because that's the word, the trigger word that starts Alexa off. So you can see here 31%. At the point at which this booklet was written, 31% from coal and peat. I think that's now a lot less, but you can look that up on the internet. So what you've got to do, you've got 2 tables, top one for the UK, bottom one for the world. Or let's swap those 2 around actually, because that might confuse you, because the world pie chart is on the left, that comes first, and the UK pie chart is on the right. So we'll put that second. So we'll do the UK there, we'll do the world there, and you've got to work out, so you're adding up percentages and get a final percentage here and a final percentage here for renewables and non-renewables related to this pie chart, and the table at the bottom relates to that pie chart. That's the end of lesson 1. Make sure you complete the plenary assessment on Study Zone. See you next time. Bye.